All right, let's take a look at exponential functions. An exponential function is defined as f of x equals a to the power x, where a is not equal to 1, because otherwise you'll just get 1 to a power, which is just 1, a horizontal line. Nothing interesting happens there. And so we're only looking at positive real numbers. Why not negative? Because remember, if you have a negative number and let's say x was half, that means you're looking at square root of negative 1 or an imaginary number. So in order to work with real valued functions, we're only focusing on numbers that are positive real numbers not equal to 1. Well, how does this graph look? So in order to figure out how this graph looks, let's just go back to our graphing and take a look. If you want f of x equals 2 to the x, then we have to plot some points. So let's plot some points. How about when x is 0? When x is 0, 2 to the 0 power is 1. So let's enter that. Let's take a look at x equals negative 1. 2 to the negative 1 power means what? Negative exponent makes it reciprocal, so 1/2. So let's plot. How about negative 2? Then it will be 1 over 2 squared, or 1/4. Remember, if you're having trouble understanding what is happening, you're just plugging in values. 2 to the exponent of negative 2, which is 1 over 2 squared, which will give you what? 1 over 4. Okay? Let's plot some x equals 1. 2 to the power 1 is 2. Plot. What about 2? 2 to the 2 is 4. And plot. And so here are some points, and now we have to connect. So let's connect them together and see how the graph looks. So there is our graph going through these points right here. Now the question is, okay, once we have this graph, now take a look at this. As x becomes smaller and smaller, like negative 10, negative 100, it almost looks like a flat line here. It never quite touches the x-axis, but it gets closer and closer. It looks here like that because we are zoomed in at this scale. If you go in a little bit closer, you'll see there's always a gap between the function and the x-axis. So this x-axis here is called the asymptote. An asymptote is a curve to which eventually, as x goes to infinity or x goes to negative infinity, in one of those or both of those places, the curve gets closer and closer to it, but never actually touches it eventually. After a certain point, the graph never touches that curve, but gets closer and closer to it. That's the quickest way of understanding what an asymptote is. So exponential function means our variable is in the exponent and the base is a positive real number not equal to 1. So that's the graph of 2 to the power x. Oh, and what happens if a was less than 1? Like a equals 1/2. Another way to write 1/2 would be 1/2 would be 2 to the negative 1. So this is the same as 2 to the negative x power. So if you are smart, you already know 2 to the x graph, which was this way. And so if x is becoming negative x, then we should expect a graph going this way. Let's plot some points and see. So for example, when x is 0, 2 to the 1/2 to the 0 power is 1. Or any real number, non-zero to the power 0 is going to give you 1. Let's say 1. 1/2 to power 1 would be 1/2. 2. 1/2 to the 2 power will be 1/4. All right, what about negative 1? 1/2 to power negative 1 will be reciprocal of 1/2 or 2. 1/2 to power negative 2 would be 2 to the power 2 or 4. All right, so if we connect, you can see it's similar shape to 2 to the power x, but it's what? Reflected across the y-axis. So let's plot this function here. And again, you can see that the x-axis, or y equals 0, is your asymptote. And so let me graph 2 to the x so you can see what happened. Here's our 2 to the x, and if you reflect it across the y-axis, you get the graph of f of x equals 1/2 to power x. So That's another way to think about how if your number is smaller than 1, then a to power x has this shape of graph. All right, let's go back to our slides. So if a is smaller than 1, then your graph is going to be of this type. And again, both have horizontal asymptote of y equals 0. So what do you think is the domain of both of these functions? Domain is all the inputs or the x coordinates for which there is a graph. So you can see that x coordinates have a graph value attached to it, all of them. So domain should be negative infinity to infinity or all real numbers. What about the range? Well, you never touch 0. So it's 0 to infinity, but not including 0. So domain is all real numbers, range is 0 to infinity, and 0 is not included because y equals 0 is your horizontal asymptote. Well, how about 1 to 1? Yes, it's 1 to 1 because you can see that any horizontal line will only contact the graph in one point here. Anything under it, there is no contact. So this function is 1 to 1, similar to this function. So they are both 1 to 1 functions. So in general, all exponential functions are 1 to 1. All right, let's take a look at examples then. 2 to the x. So what if I gave you f of negative 1? We just saw when we plotted points that that would give you 1/2. F of 3 would be 2 to the third, or 8. F of negative 3 would be 2 to the negative 3, which would give you 1 over 8. And we actually used this information to plot our graphs. F of a plus h would be 2 to the power a plus h. What does that really mean, 2 to the power a plus h? 2 to the power a times 2 to the power h. That's how you add exponents. All right, piecewise defined functions. So here, piecewise defined function is exactly what its name suggests. It's defined by 2 or more equations for different parts of the domain. So let's take a look at f of x equals the following function. It's defined into 3 pieces here. You have the output value is 1 for all x values between 0 and 1, including 0. Output value is 0 if your input value is anywhere between -1 to 0, including -1. And your output value is -1 if you have -2, so that's equals x less than -1. How would that graph look, do you think? Do you think you can plot it? Why don't you pause the video here and on your own play with how that function would look. All right, so let's plot the graph and see. When x is 0, you have 1, and all the values between 0 and 1 have value 1, except at 1 you have a hole, because at 1 is not included in the domain. -1 to 0, -1 gives you 0, and 0, there is a hole because in this piece, 0 is not included. And then same thing with this piece. So let's take a look at the domain. Remember, domain is all the x values. So anything below -2, no graph. Anything above 1, no graph. So you can see how we have pieces. So this is sometimes referred to as step function, because you can see how it looks like step. So our domain is going to be -2 to 1. Be very careful now here. Look, see this coordinate here is not included, but it is included here. That's why we can go all the way from -2 to 1. Sometimes the domain could also be in pieces itself. It may not be all one continuous interval like how we have here. All right, range. Well, range is not even interval, it's just discrete points, because all the values here take on value of -1. Everything here takes on the value of 0. Everything here takes on the value of 1. So -1, 0, and 1 are the real numbers that form our range. What if I ask you to evaluate function values? Like, say, f of -0.5. Well, first we have to locate -0.5, which will be here. -0.5 falls in this one. If you're just looking at algebraically, -0.5 falls in this category, and so we'll have to use this second rule. So f of -0.5 is going to be 0. What about f of 0.5? So pause the video here and you do the remaining 2. Because we already told you that the first one is going to be 0. pause the video and you do the other two. 0.5 falls in the first rule, good. And what about negative 1.5? That would fall in the last rule, so that'll give you negative 1. So it's important to understand how to evaluate piecewise functions by looking at which rule fits it. So if your input is in this, then this will be the output. If your input is here, then this will be the output.